do it again and again and again until convergence. But if you have a large model and a large data set, then that's just a really slow process. If you think about, if you have some examples in your data set that are similar, they're inducing similar gradients on your network, then it's really just inefficient and redundant to be calculating these gradients, averaging them all together across the entire data set. You're much better off doing it in batches, as I'll show you. So, yeah. So in normal gradient descent, when you go across the entire data set, you're getting a very accurate estimate of the gradient of the loss function at that point. But it doesn't really matter how accurate it is. It's very slow. So what instead you should do is mini-batch stochastic gradient descent. So normal stochastic gradient descent is, I'm going to feed in one example and get the gradient of the loss with respect to all the weights for that one example. Now what we're going to do is feed in a mini-batch, or a batch of examples. We're going to get the gradient for that batch, then use that to update the weights. And then at the end of each epoch, after we go through the entire data set, we're going to shuffle our weights, or sorry, shuffle our examples, and then we're going to use this new ordering of examples to train. So you can think of this as giving a noisy estimate of the gradient at each time step, but often it's good enough. You know, even if your gradient isn't exactly perfect, as long as it's in the right direction, that's still getting you out of whatever kind of landscape that you're in the optimization space. And this noise is actually helpful in cases of getting you out of kind of local minima, because if you have a noisy signal that's sending you all over the place, then if you happen to be stuck at kind of a plateau in a loss function, then it can actually send you kind of in different directions and get you out of those a little more quickly. Yep.
Are there cases where like full-size gradient descent works, but stochastic gradient descent doesn't work?
No. Typically, as long as you use a batch size. Okay. So if your data set was like so small, or you had like very unique examples, then it would mess you up if you use stochastic gradient descent. But what you're doing with using stochastic gradient descent is saying, I'm going to assume that the distribution, if I take enough examples, is going to be pretty much the same no matter what for my gradient. And so if you were to use stochastic gradient descent, but you had really just examples that varied quite a bit, and it was like an ordering to them, then yeah, it would send you like in the wrong direction at one point, and then in another direction at another point. But yeah, as long as you have kind of a roughly uniform data set, you should be fine. So one thing that, if you haven't really thought about this yet, training a deep network is a non-convex optimization. So I don't know if Yusong's gone over this, but basically a convex optimization problem has a unique global minimum, and assuming you have an appropriate learning rate, you can get there. It might take a while, but you can get there. Non-convex optimization, there are no guarantees. You might end up in a local minimum. You might go around the surface for a while and end up in a really bad local minimum. And so you might end up with a solution that's just not very good. But should we be worried about this? And the consensus at this point is no, not really. These optimization landscapes tend to be full of saddle points, but not really like wells. So what that means is that there's a lot of points at which moving in a bunch of directions will send you back to where you came from, but there's often a particular or at least a few directions in the weight space that can send you out of this kind of flat area in your optimization space. And so the trick is really, I'm going to end up in a lot of saddle points. How do I identify how to get out of this saddle as quickly as possible? So there's been a lot of actually, I'll go through this real quickly. There's, like, why is a neural network non-convex? And it's really because of the nonlinearities. Imagine we were to remove all these nonlinearities. Now you're just applying a matrix after another matrix after another matrix. And what you end up with is just, you can just collapse all those matrices down into a single matrix. It's just then a linear classifier at that point. So it's really the nonlinearities that are messing us up. So in vanilla stochastic gradient descent, you apply the typical terms, but when you add in this extra term called momentum, that can help to speed up things immensely. So you now take input from your past gradient updates to inform your current gradient update, and you keep kind of some momentum of how you were going before. And so this helps to send you kind of as like a ball rolling down a hill with a little bit of a push. And so this tends to converge much faster, and you can kind of think about it in these simple diagrams of just sending you kind of in the correct direction a little bit more quickly. So there's another issue, which is, we still have to set this learning rate. How do we do that? Should we have the same learning rate for all of the parameters? Should we modify it? Kind of this thing we were talking about before. And there's a number of different optimizers that have been developed over the years to attack this problem. The first was kind of AdaGrad, where you are now keeping a running kind of total of the weights, of the updates that you've taken, and you are going to use this to inform your current gradient update. And then other methods have kind of improved upon this, and kind of the gold standard at this point is this optimizer called ADAM, which is stands for Adaptive Moment Estimation. And so there's these cute little visualizations of these different optimizers working through a saddle. So there's that one, and then there's, so you can see, some of them just get stuck in these saddle points. They can't get out, because if you think about it, the gradient is very shallow at this point. How do you know which direction to head in? But if you have a little bit of momentum, a little bit of memory in how you've been updating your weights, then that can go a long way in actually getting you out of these things faster, and they're quite helpful. So let's talk briefly about some perspective on deep learning, because I think a lot of people see the current kind of deep learning craze, and they think, oh my God, like we finally figured out AI. This is just, this is kind of a new thing, but it's really not. This goes back to like shortly after computers really became popular. So back in the 50s was when the perceptron was developed, and this is a physical implementation, like a hardware implementation of a perceptron with a bunch of wires. And this was back in the 50s, and people were thinking about these problems. People were thinking about, okay, I'm going to try to build an artificial neuron. I'm going to try to build a computer that thinks like a human. And you have even like people like Claude Shannon, who were saying back in the early 60s, in 10 years, we're going to have computers that are the stuff of science fiction. These things are going to be like, it's like general artificial intelligence in 10 years, back in the 60s, people were saying this. But that didn't turn out to be true. And actually what happened is the field entered into what's called kind of a neural net winter. And so this happened kind of starting in like the late 60s, 70s. People were saying, all right, forget this neural net stuff. We'll never figure this out. Let's just go to this rule-based AI. We're going to hand program it. It'll work. But it didn't work. And so then in the 80s, people started to think about neural nets again. And so there was this model called the neocognitron that was very popular. You couldn't train it, but it was very popular. Kind of a demonstration of, maybe neural nets could work if you had enough layers of them. And then finally in 86, people said, we finally have figured out backpropagation. The funny thing is, though, that it had been independently derived like 5 times before that. People just did not realize it at that point. But this paper in 1986 was like the paper that made it mainstream and popular. But this backprop was developed back in like the late 60s, again in the 70s, again in the early 80s. Like, it was developed a bunch of times. People just didn't really quite get the hold of it. And then in the late 80s, convolutional neural networks were developed. So I'm going to be talking about these on Tuesday. And so these have this nice kind of like property of, they work well with images because they have this notion of kind of a spatial invariance. So we'll talk about those more. And then another neural net winter. That happened in the kind of the mid to late 90s through the early 2000s. And at that time people said, neural nets, they have these vanishing gradients, we have no idea what's going on, let's all use SVMs forever. And it didn't quite, at a certain point people realized again, neural nets are actually quite popular. And so it was really around 2006 that some big breakthroughs started to happen where people were using kind of a per layer training scheme in order to train very deep networks to do like digit classification. So these results weren't groundbreaking, but they were at least showing, okay, you can train a deep network. In 2009, really is when people started to use these GPUs for research. So a GPU is just it's a graphics processing unit. It's made for handling graphics kind of processes where you're trying to update a bunch of pixels. And what these cards are really good for is, unlike computers which have a lot of cores and are like weakly parallel, these cards are actually highly parallelized, great at doing things like matrix multiplication, which is exactly all that neural nets are. So these things were like the most amazing invention to all these researchers. And all of a sudden, you see all this neural net research being done. And in 2011, people were training unsupervised networks to watch YouTube. And they figured out what a cat is. Some groundbreaking research there. And then in 2011, again, there was some breakthroughs on modeling speech. So I might talk a little bit about that on Tuesday as well. And then in 2012, this was like the most amazing thing that had ever happened because finally we had the data, we had the hardware, and we were able to classify objects pretty well. So we were able to train a neural network to classify objects, and this more than halved the error rate of the next best approach, which was not a neural net. And since then, it's just been a deluge of neural network research coming out of academia and industry, and you've seen things like neural Turing machines, you've seen deeper and deeper networks, deep reinforcement learning for the game of Go and for Atari. Really just people finally have the tools to do this research. They're finding some very, very amazing things. So what really was driving this boom? The hardware and the data, primarily. It wasn't new techniques as much as it was these factors. Once you had these factors, people could do the experiments and actually develop better architectures, and then people start to develop these libraries. So make it very clear in your mind that you need data and hardware first. The other stuff will come after that. These are kind of like the main people that helped to develop deep learning and keep it alive during that second neural net winter. But there's a lot of other people along the way that had a lot of contributions. But Geoff Hinton is kind of considered the godfather of machine learning. It's kind of a weird title, but that's what he's considered. Yann LeCun developed convolutional neural networks. He's kind of a big shot. He's the head of AI research at Facebook. And Yoshua Bengio is a researcher at the University of Montreal. And he's pretty much a big shot as well. And their citation numbers have just been exponentially growing since deep learning became a big thing. But so it's important to look back and think, okay, so there's this boom-bust cycle that happened in deep learning where there's a technological breakthrough, there's some excitement, and then there's hype. which is, we're going to finally solve intelligence. It's only 5 to 10 years away. Don't even worry about it. And then it inevitably doesn't live up to the expectations. Funding dries up, and then people move elsewhere, and then it repeats. So it's really important, and one thing I want to just impress upon you is that you shouldn't just believe the hype. Hopefully I've demystified neural networks quite a bit, and hopefully you don't think it's all hype. So is this time any different? Sort of yes, sort of. So it's obviously impossible to say what's going to happen in the future. One thing that is for certain, though, is that these neural networks are finally commercially viable. All these major corporations are using deep learning and making money by using it. So it seems at least that no matter what happens, at least these corporations are going to be pouring money into it. There's going to be a need for this research. Academia is going to be there. So it seems like it's here to stay. But do beware of the hype, because human-level AI is not just around the corner. And saying something that's 5 to 10 years away, really somebody's trying to tell you that they don't know when it's going to happen. And don't believe people that tell you that deep learning works like the brain. It really is only a very superficial resemblance. And just because somebody has some cool graphics, it doesn't mean that they're accurate. I can't tell you how annoyed I get when I see computer chip brains, oh, we finally figured out intelligence. No, you haven't. So I want to just address a few arguments on both sides, and then we'll be out of here shortly. So on the side of the non-believers, they say, this is just a passing phase. Deep learning, don't even get involved with it. It's nothing but trouble. And so their arguments are this, that we really don't have a good intuition for how it works. We don't have a good intuition for how it learns, that these models are just like black boxes, and it doesn't actually work like the brain. And despite what people will tell you, it's not actually working like the brain. There's some big differences. On the side of the believers, they're going to say things like, this is the dawn of general AI, and we're breaking benchmarks. How could you not believe in this approach? You're going to learn your features instead of hand-coding them. Doesn't that sound great? And it's biologically inspired. But really, so let's think realistically about deep learning. So really all it is a method of approximating these really complicated hierarchical functions, and AI tasks just happen to be made up of these functions. It's just a tool for linearizing nonlinear data, and it actually doesn't replace other machine learning methods, it just enhances them. You still need to learn your machine learning basics. This is just giving a more expressive function kind of on the back end of that machine learning approach. We really don't know, what do they learn? How do we train them more efficiently? Or really, how to build them in the first place? We really don't have the intuition for doing these things. There's a lot more work to be done. But I assure you that any approach that eclipses deep learning and becomes the new hot thing is still going to involve some hierarchy. You're still going to have to learn these features. They're just too complicated to code by hand. And it's going to have a lot of parameters. You can't just fit simple functions to really complex data. So those things are certain. So when should you use deep learning? Well, the first thing I would tell you is try something simple first. It's not a good idea to go for the most complex thing. Often a simple thing will work better than a more complex thing. And it'll be easier to get working. So you should really only use deep learning when you have enough computing resources and enough data to train a model. If you don't have the data, forget about it. Really, you're just learning by sectioning up a nonlinear space. So think about, does your problem actually have this hierarchical aspect to it? And another question would be, why not make a deep learning version of some other machine learning approach? Why not just use boosting or something like that? And the answer is, you could. There's nothing stopping you really, from learning a hierarchy of some other like basic function. And that would probably work pretty well too. But the main thing is that these deep networks are trainable. You can fully differentiate all the way back through them and train this large function. With a lot of other approaches, you just you can't make this depth and train them. So that's really the only reason why people are relying on deep learning so much. So in the next lecture, we're going to talk about convolutional neural networks. These have taken the computer vision community by storm. I was at the Computer Vision and Pattern Recognition Conference this past summer, and really all of the submissions involve deep learning in one way or another. That's what computer vision has become. But it's funny because a lot of these deep learning approaches were shunned about 10 years ago. It used to be that you could not get a paper into the International Conference of Machine Learning or the Neural Information and Processing Systems conferences if it had a neural network in it. You just would not be able to get a neural network paper published. But now it's all deep learning, which is pretty crazy if you think about it, how quickly the field has changed. So we're going to be talking about kind of what it is about these models that makes them suited for images. We're going to go through all the details, and I think the homework is going to kind of touch on training some of these models, and hopefully you'll get some better intuition. So that's all I have.